All right, just like we did for derivatives, the integrals for e to the x follow the same pattern there. So the derivative for e to the x is just e to the x. So if I integrate e to the x, I'm also going to get e to the x. The part where it's going to be different is if this exponent is something other than just plain old x, you're going to have to do some u substitution first. All right, it's going to give you a coefficient in front of the integral. So if you look at the first example there, my exponent is something other than just plain old x. So I'm going to let u equal that exponent. The derivative of u is du. The derivative of 3x minus 1 is going to be 3 times dx. I need the dx in the problem. I don't need the 3. So we'll put the 3 on the other side as a 1/3. And now I can rewrite this integral all in terms of u. So I have e to the, instead of 3x minus 1, I'm going to make it u. And dx I'm going to take out and make it 1/3 du. We'll put the 1/3 in front of the integral. If you integrate e to the u, you're going to get e to the u. And then finally take out that u and replace it with what u is equal to in terms of x. All right, so you have to do u substitution. A lot of times u would be the exponent for these exponential functions. Not every single time, but it's a good place to start. So if you look at the second one, if you let u equal, like we said, the exponent, the derivative of u is du, and the derivative of negative x squared is negative 2x dx. I need the x and I need the dx, but I don't need this negative 2 out in front here. So we'll put it on the other side. And now I can rewrite this all in terms of u. So I have e to the negative x squared, which is e to the u. The x and the dx I'm going to replace with negative 1/2, negative out there, and it's du. And now you can integrate. E to the u integrates to e to the u. Take out u and replace it with what it's equal to in terms of x. You can leave your answer just like that. The next one, we've got some trig in here, so we can go through and integrate that. Same idea, if we let u equal the exponent, we're probably going to pick up the other pieces that we need. So if I let u equal cosine x, the derivative of cosine x is negative sine x. And I need a positive sine x, so we'll put the negative on the other side of the du. Right, rewriting all in terms of u, I have e to the cosine x is equal to u. And then sine x dx, I can take that out and replace it with negative du. And e to the u integrates to e to the u. That negative out in front stays there. And finally take out u and replace it with cosine x. All right, number 4 is the same idea, but now I have bounds of integration in there. So I have just one more step at the end here. So if I let u equal the exponent, du gives me negative 2x dx. I need the 2x dx, I just don't need the negative, so we'll put the negative on the other side. If I rewrite in terms of u, e to the negative x squared is u. The 2x and the dx I can replace with negative du. E to the u integrates to e to the u. No plus c this time because we have bounds for integration. Let's take out the u and replace it with what it's equal to in terms of x. And then we'll plug in those bounds from 0 to 1. So if I plug in the upper bound, I have negative 1 that's squared, minus, if I plug in the lower bound, negative e to the negative 0 squared. So let's see, I have negative e to the negative 1 minus a negative e to the 0. Well, e to the 0 is equal to 1, so it's minus negative 1, which is plus 1. All right, and then finally the last one is just a fancy way of saying find the area under the curve from negative 1 to 0. So I'm looking for this area right here. If I integrate from negative 1 to 0 and my curve was e to the x, cosine of e to the x, and I'm integrating with respect to x. So for this one, I'm not going to let u equal the exponent, because then I'm just going to have the same problem. I'm going to have e to the u cosine e to the u du. It's exactly the same problem. So that didn't help me any. So I need to let u equal something else then. So let's try letting u be the e to the x. And the derivative of e to the x is also e to the x. What that does is that lets me rewrite this cosine of e to the x is cosine of u. And then the e to the x and the dx in the beginning and the end I can rewrite as just du. So now I have something I can actually integrate. If you integrate cosine, you get sine. Take out u and replace it with e to the x. And then I'm going to plug in my bounds from -1 to 0. So I have sine of e to the 0 minus sine of e to the -1. You don't have to do a lot with this. So e to the 0 is equal to 1. And this sine e to the -1 or 1 over e, whichever you like, you can leave it just like this. That's an exact value. If you put it in your calculator, just make sure that you're in radians. All right, you can get a decimal estimate for it. But this answer is fine. You can leave it just like that.